All right, let's learn a little bit about nuclear chemistry together. In the previous chapters, we talked about chemical reactions, and all the time we emphasized on electrons. But the difference between a chemical reaction and a nuclear reaction is that in a nuclear reaction, we're talking about the nuclear changes that happen and they are independent from the environment around the atom, while chemical reactions are depend on what atoms are surrounded by. Uh, just like any other topic, you need to know a little bit about the terminology. Like you need to know about the radioactive decay that we will talk about it later again. We will work on it in details. Radioactive decay. Decay, you've all heard about the radioactive decay or maybe carbon dating. It's a process that nucleus spontaneously disintegrates or spontaneously decays. So a part of the nucleus starts disintegrating. Also, we have some nuclear reactions. We call them nuclear bombardment reaction. Bombardment reaction. You bombard the nucleus of the atom and the atom will change. The nucleus is going to change to another nucleus or another particle. So you have the apparatus on slide number 12. There are 3 different radiations in nuclear chemistry. The first experience of radioactivity was discovered by Henry Becquerel. He was a photographer, as far as I know, and he found out that photographic plates, the old school type of photography, they had some bright spots on them. When he put some uranium minerals in the same drawer next to his photographic plates. So he found out like that these uranium minerals must have radiated something that affected the photographic plates, his negative. According to the type of radiation, we have 3 types of radiations: alpha rays, beta rays, and gamma rays. You need to use them the way it is, and we will talk about them in details. What is the nature of each one and how use them in the nuclear equations. So, and a very common equation in nuclear chemistry, as you have it on slide number 13, I go with the same example. When you have uranium, and we're talking about different isotopes. In Chem 1, you remember, you learned about different isotopes. Isotopes are atoms of the same element with different number of neutrons. N was different. So the difference appears here. So you can have uranium-235. The atomic number is the same. The difference is the atomic mass. And because the atomic number is the same, you distinguish the different isotopes by using their atomic mass. So you call it uranium-235 and uranium-238. So between uranium-235 and uranium-238, it was found that uranium-238 has radioisotope or radioactive nature. So when it disintegrates, it changes to thorium, another element with 234 atomic mass, and atomic number is going to be 90, and also a helium atom is going to release. And we will learn that we call it alpha particle later when we get it. Okay, we have it here. Speaking of it, it's gone. Try to keep these in mind. For a proton, the symbol is, or you just simply show it as proton. A proton has one proton and no neutrons. That's why we call it proton, because it only has one proton. Neutron, you knew about this particle so far. Neutron, you show it with lowercase n and 0 as atomic number. Doesn't have any proton, but its atomic mass is 1. Electron, it has a -1 charge and no mass. Or now, since we are in the nuclear chemistry chapter, we can call it beta particle. So from now on, when we say beta particle, means electron. And the symbol is this. Positron. Positrons are the opposite of electrons. It's the same electron, but instead of a positive charge, it carries, instead of a negative charge, it carries a positive charge. We call it positron, kind of like you can remember it as positive. So it's an electron with a positive charge, so we call it positron with +1. Or we call it, you show it as, again, beta particle, but negative is positive here now. Then you have gamma photon or gamma radiation. Gamma, you show it as no charge, no atomic number. And since we are talking about different particles, let's talk about alpha particle also. Helium atom or alpha. Right. So it's helium with a 2 or 4, or you show it as alpha. So these that you need to keep in mind. These you already know almost, but the electron, positron, gamma, and alpha, you need to know them the way we need it for our equations in nuclear chemistry. So as you see, beta particle is an electron. So beta particle is electron. Beta emission, sometimes we have beta particle or electron emitted from the atoms. So an electron is ejected, is coming out of the atom. Positron is similar to electron, as we said, but it has a positive charge. So electron has a negative charge, but positron has a positive charge. So you see beta and positron. I'm just emphasizing, I'm just repeating them. And a gamma photon is the particle of electromagnetic radiation. It has higher energy. If you consider the electromagnetic spectrum, if you look it up, you will see gamma photon has a smaller wavelength or higher energy than X-ray. It's closer to X-ray. It can penetrate better, and it's good for especially disinfectants, as a disinfectant for medical supplies. All right, we are at the point of doing an example about this stuff. So slide number 16 of your book has this example. Radon-222 is a radioactive noble gas. So radon, and we put the atomic mass on top. That is sometimes present as an air pollutant in homes built over soil with high uranium content. So uranium-238 decays to radium-226, which is in turn decays to radon 222. A radium-222 nucleus decays to polonium-218. So it changes to polonium-218 by emitting an alpha particle. Write the nuclear equation for this decay process. So radon, if you look at periodic table, its atomic number is 86. Polonium is 218, it said 218, and its atomic number is 84. And it says it emits an alpha particle. And I just told you that alpha particle is shown as 2 atomic number and 4 atomic mass. Very soon, when we start balancing these equations, you will see that both the masses on each side, atomic masses on each side, and atomic number, the overall atomic number on each side should be the same. 222 is equal to 218 plus 4, and 86 is 84 plus 2. So this is the way that we balance our nuclear equation. Instead of coefficients that we had for chemical equations, now for nuclear equations we must have the same atomic masses and atomic numbers. The total of atomic masses and atomic numbers on both sides should be the same. Another example on slide number 18. Iodine-131 is used in the diagnosis and treatment of thyroid cancer. This isotope decays by beta emission. What is the product nucleus? So iodine, it says 131. Look at periodic table. Its atomic number is 53. Atomic number of iodine is 53. Okay? So it says it emits a beta particle, right? So beta particle is which one? Beta is -1 and 0, correct? Now we have the product which has a Z and A. Do you remember atomic number? We showed it with Z, and atomic mass with A, CHEM-1. So now the total of these two must be equal to 131, and the total of these two must be equal to 53. So 131 is equal to 0 plus A. So what is A? 131, right? So instead of A, you put 131. And instead of 53 is -1 plus Z. So Z is going to be 54. So atomic number is 52. And you know that we locate the elements in periodic table by their atomic numbers. Which element is element number 54? It's xenon. The noble gas xenon, if you check with the periodic table. That's how you find the missing elements or missing particles in the nuclear equations. So this is the first thing you need to know. First, you need to know these really well, memorize them. And then, if you need to find a missing element or particle in the equations, then you can easily just go by the atomic masses or atomic numbers. Okay. The next concept to learn in nuclear chemistry chapter is nuclear stability. Nuclear stability. So the stability of a nucleus is because of a strong nuclear force. There is a force inside the nucleus of each atom. Is called nuclear force. This nuclear force works for very short distances. We're talking about the atoms, the tiny atoms, about like 10 to -13 meters, okay? For short distances. for about like 10 to negative 13 meters only. And at this distance inside the nucleus, this force is stronger than the electron repulsion. So this force is going to be overcoming the electron repulsions. So the same way as we had the shell model for the model for the electrons, we have the same thing. Electrons, you remember, they were on the different energy levels. We have a similar model for the nucleus. We call it shell model of the nucleus. Shell model for the nucleus, that proton and neutrons exist in levels. Very similar to shell structure that we had for electrons. We're not going to talk about this shell model. Let's talk about the magic numbers. You need to memorize some numbers. Magic numbers is the number of nuclear particles in the shell of proton, in a completed shell of protons and neutrons. You remember we had, like, for shell 1 or level 1 we had 2 electrons, for level 2 we had 8 electrons, level 3 we had 18, and level 4 we had 32. Now here, for the magic numbers for the number of nuclear particles, is that for protons we have 2, 8, 20, 28, 50, and 82. So a little bit of memorization will help you here to solve the problems regarding the nuclear stability. So 2, 8, 20, 28, 50, 82. The number of neutrons, we're talking about both of the nucleus particles. 2, 8, 20, 28, 50, the same. Instead of stopping at 82, we also have 122 for the neutrons. So you need to remember these numbers for the exam. So if you pay attention to slide number 24, you see that there is, when you draw a plot of number of neutrons, you have a beautiful graph on slide number 24. I'm just trying to imitate it. So versus the number of protons. Protons are shown as Z and neutrons are shown as N here. So if consider the nuclei with number of neutrons equal to protons, we call it the band of stability. Okay? Then you will see some of the atoms are around this and some of them start deviating from this band of stability. So it shows that this is the band of stability when N and Z are equal. When N and Z are equal, it gives a stability because the ratio is very close. When N to Z is very small, N to Z, the ratio here is small, it's less than 1.5, very small. So the type of emission we talk about them is positron emission or electron capture. So let me write it here. For N over Z, very small, then we have positron emission. What was the sign for positron? Remember, it was like electron, but instead of -1, we had a +1. Positron emission. Okay, or electron capture. So atoms with this very small N to Z ratio, they tend to have this type of, to go under these types of reactions, the nuclear reactions, either emit the positron or capture an electron. But when N over Z is large, then you normally have beta emission. Beta emission, what was the beta emission? Right, electron or beta emission. Okay, so keep these in mind. Some atoms are around this stability band, but the rest of them are not. They start getting farther from the stability band. So when Z is, or atomic number, when atomic number is smaller than or greater than 20, equal to 20, then the ratio of neutron to protons is between 1 and 1.1, which is not very much, is small. And for a stable nuclei with, when Z is more than that, the ratio of neutrons to protons is about 1.5. So because by increasing this ratio, the number of protons increases, then there should be the repulsion increasing between the protons. Don't forget, protons have a positive charge. Then we need more neutrons to increase the strong nuclear force. Neutrons don't have a charge. They don't have any role in balancing the charge. They just increase the nuclear force. And also learn something for Z above 83. For the, you remember the last proton was 82? So for above 83, there is no stable nuclei. No stable nuclei. By the way, nuclei, if you didn't know, is the plural form of nucleus. So now let's work on an example based on what we just learned. Slide number 26 is asking us predict which nucleus in each pair should be more stable and explain why. Astatine 210 and lead 207. Astatine 210 or lead 207. If you look them up in the periodic table, lead 207, it has 82 protons. And the number of neutrons in it is 125. For astatine, we have 85 protons. And neutrons is the same, 125. So which one has a magic number? This one plus astatine has 85 neutrons, which is more than 83. Didn't we just say when the number of neutrons is more than 83, the nucleus is not stable? So lead 207 is more stable. The next one is molybdenum 91 and molybdenum 92. MO91 or MO92. Then look it up at the periodic table again. It has 42, 91, it has 42 protons, 49 neutrons. 42 protons and 42, okay, 49. No way, it becomes 91. More neutrons. And molybdenum 92 has 42 protons and 50 neutrons. So molybdenum 92 is more stable because it has a magic number of neutrons. It's almost 50, so all right. And finally, calcium 37 and calcium 42. Calcium 37 and calcium 42. Calcium 37 has 20 protons, and so it must have 17, right? 17 neutrons, yes. And calcium 22 has 20, calcium 42 and 22 neutrons. So calcium 42 is more stable because it has an even number of neutrons, and the balance is better between these two, 20 and 20, to the N to Z ratio is better. All right. Let's talk about different types of nuclear reactions. 6 common types of radioactive decay. You need to know these really well because of the questions you might have on this part. So, types of decay. Radioactive decay. Let's write it complete. The first type of radioactive decay is alpha emission. Alpha emission. What was the sign for alpha? Helium 2, 4, or you can show it as alpha 2, 4. The example, when there is an alpha particle from an unstable nucleus, is going to be emitted to be the product. So like radium 226, its atomic number is 88, and it breaks to radon 222, and 86 would be its atomic number. So if we want to balance out, how many do we need to add to 222 make it 226? 4. And how many we need to add to 86 to make it 88? 2. Atomic number 2, atomic mass 4 belongs to alpha particle. So you can write it as helium or alpha. The second type of decay is beta emission. We had alpha emission, now we have beta emission. What was the sign for beta? It was either electron, or you can show it as beta. So you have an emission of particle, beta particle. When you have carbon 14, it changes to nitrogen with 14. So what should be the mass of the particle? 0, because it's already 14 and 14. How many do we need here? Well, how much do we need here to make it 6? We need a -1, which is the same as electron. Also, it's equal or equivalent to when a neutron, that's neutron, right, emits an electron. So what is the other particle here? 0, so we need the 1. This is -1, so we need the 1. So which particle has 1 and 1? Proton. So also, if neutron emits a beta particle, it will change to a proton. Isn't it interesting? All of these happen in the nucleus of an atom. The third type of decay, and by the way, all of these can happen during hundreds of years, not just in 1 second. We can have each of these emissions over and over and over during centuries. Next one is positron emission. What was the sign for positron? By now you should know it. Positron was the electron, but with a positive charge, right? Oops. Or you showed it as this, right? So technetium is one of the heavy elements, 95. And if you pay attention, we choose most of them, not all of them, most of them from lanthanides and actinides from the heavy elements. So it changes to molybdenum 42 and 95. So what particle do we need here? It should have a 0 mass because we already have the 95 valence, and a 1 here, which is electron emission, positron emission. Or it is equivalent to when a proton emits a positron. So we must have a 1 as the mass and a 0 here, which is neutron. So when a proton emits a positron, then it will change to a neutron. Fourth type of decay. Fourth type of decay is electron capture. Electron capture. So far, these particles, electron by the way is this, right? So far, all of the particles were the product. Now, when we say capture, means that electron is our reactant. For example, potassium, if it grabs an electron, then it would change to 40, I'm balancing it, right? And it would change to 18. Which element is number 18? That's our famous argon. Or if a proton captures an electron, changes to 1 and 0, right? What is the particle with 1 and 0? Neutron. A proton with a positive charge added to electron with a negative charge, they are balanced with a 0 charge. The fourth type of emission is, the fifth type of emission, sorry, is gamma emission. Gamma is this particle with 0 and 0. So nothing happens to the mass or atomic number. You only excite the electron emission from an excited nucleus of a gamma photon, then with a wavelength of very low wavelength, like 10 to negative 22. So if you have a gamma emission, you have the same X with Z and A, changes to X to Z and A, but a gamma particle will release. So if you have a question that which of these emissions does not change the nature of the particle, you will choose the gamma particle. So it just is about the excited atoms. And finally, the last type of radioactive decay is spontaneous fission. Spontaneous fission. So when an unstable nucleus with a heavy nucleus of mass number greater than 89 splits into lighter nuclei. It's kind of like the same as decomposition reactions that you learned about other elements, other reactions and compounds, but now you have a nuclei, so a heavier, like let's say uranium-236 will decay, will go under fission that changes to terbium plus iodine 136, and if you balance it out, 136 plus 96 and 53 plus 39, then you will have 4 neutrons also emitted. So it's like breaking the heavier elements to the lighter nuclei. So, yep. You can work on the example here now. Thallium-201 is a radioactive isotope. I'm talking about slide number 37. Used in the diagnosis of circulatory impairment and heart disease. How do you expect it to decay? Thallium, TL-201, has 81 protons and 120 neutrons. So N2Z is smaller than 1.5, so this is a small. We said for the elements, for the nuclei with N2Z less than 1.5, then we have either electron capture, or positron emission. We go back to previous slides, we have it, or to the previous slide to this, or electron or positron emission. In the next video, we will talk about radioactive decay more, and we will work on some calculations.